Good morning. Welcome to Beersheba. Welcome to Ben-Gurion University. We are starting our first session with our distinguished guest, keynote speaker, Dr. Gautam Shroff from Tata. Please.
It's a pleasure to be here. I was in Israel about 12 years ago. Probably this university was just getting started, or certainly not as big and prospering as it is today. And what I'd like to speak about today is the way business intelligence is evolving in the current age of digital technology. Essentially speaking from the experience of dealing with our customers, who are essentially the Fortune 1000 companies in the world. Brief introduction to Tata Group and TCS, where the Tata Group is the largest industrial group in India. We have over 100 operating companies, ranging from chemicals to engineering, including automobiles, energy, power, distribution, telecommunications, and information technology. TCS is the information technology company, which is the largest software services company in India, and is currently one of the leading ones in the world. Where the numbers are fairly daunting, at least from the numbers of people perspective, for sure. Over 300,000 people, hundreds of more than 100 countries represented among them, and we've been around for a long time. As a result, we also have research. We've been doing research in computing and related areas in TCS for more than 35 years. We have a number of labs. We have an advisory board, including Jeff Ullman, who was here yesterday, V.S. Subramaniam, who's well known to Braha, and others from the Indian academia. We have 7 locations in India. I am personally located in Delhi. We also have a location in Cincinnati in the US, primarily to deal with our manufacturing customers. And as we grow, we will hopefully have locations in other parts of the world. In terms of how we're organized in TCS Research, and this sort of gets into what the kind of research that we do, the core research area we started off with was software engineering, software architecture, and out of that came a whole bunch of tools which are now productized, and out of that have come our entire suite of financial products business, which I haven't put on the chart, but that's now more than $500 million in business today for us. We have a systems research, which is all about computing systems, IT, data centers, security, privacy, communications, and related areas. And out of that, in the past, have come our cloud platform, which serves over 500 small and medium businesses in India. It's the one and only, essentially, business cloud platform in India. And it also runs all our central examinations across literally hundreds of thousands of students across the final year of school, the entrance exams for various colleges like the IITs, the medical. All of that is run on our cloud platform today, plus a whole bunch of verticals in different parts of different areas. So this first part of research is really about the industrialization of software and computing, making software computing more automated, more reliable. So cloud, tools, and e-transform, which I just left out there, is all about automating the data center for those who don't use the cloud solution, but the large companies who have their own data centers. Applications is the largest research area today, which is where I spend most of my time. Digitization of industry and society, which is the other side of what is happening in the world as computing gets automated, so that society is also getting digitized, and industry as well. And in there we have sort of developed a number of things in terms of the Internet of Things, connecting cars, connecting instruments of all kinds, and also an example is Perivista, which is our connected platform for analyzing customers from 360 degrees. So I just wanted to mention these as that the research is not in isolation in TCS. It does come out with the business impact. A few of them which are business units have their own logos, others which are on the way are sort of represented more as the ones below. And there are many more. But I'm not going to talk about that in great detail. I'm going to talk more about what we're doing today. So what do we see in the world of IT? We see our customers thinking about four things really. On the one hand, there's a whole bunch of emphasis on simplification. IT systems are becoming very complicated, and therefore all kinds of technology to automate processing of data centers, of trouble tickets, of management and maintenance of IT is critical. Governance, risk, privacy, security, all that is becoming very important. And also is sustainability in terms of energy, in terms of social impact, in terms of making sure that one is doing good for the society. All that is just as important for most of our customers. But I'll talk a lot about today about digital reimagination, which is the main topic where most of the data mining, business intelligence work is getting applied. So what is digital? Digital really talks about, it's a trend which you can see, probably hoardings in many airports, many IT companies talk about digital. What is it? So it's really about the Internet of Things and social media, which are producing a whole bunch of data. And big data, which then needs to be analyzed, and the results of that in terms of better services or more targeted solutions are delivered to customers and consumers using mobility and cloud computing. So what does that really mean? So this is, I think I'll spend a little bit of time on this because this sort of is what we are seeing our customers transform themselves, not just technologically, but from the nature of the business that they do. Start with banking and financial services. I think everybody here has a bank account, right? So all your money is just bits and bytes. I mean, the cash is very small, and everything is really numbers. And the banks are really the first IT company. I mean, the bank doesn't exist without bits and bytes, right? Without computing shuts down, money goes away, right? So essentially, a payment and storage hub for money is what banks are. Right? But they make their money by lending your money to others. That whole model is getting disrupted. There are many companies now which are allowing you to lend directly to consumers, to borrowers, and many other. There are startups which are getting involved in giving financial advice. There are startups getting involved in many aspects of banking. PayPal, the whole payments area is getting disrupted. Telecom companies are getting involved in payments. So what does a bank do? So bank has a lot of data. Bank knows who buys what, when, how often, what kind of people buy what. And so their customers are also merchants. So one of the things that banks are trying to do now is becoming advisors to their merchant customers. So they are actually trying to help them market better to all of us, help them target their product mix better, help them decide what to market where, which is a very different thing for a bank. A bank was never used to this. So that's one thing happening in banking. Insurance. Insurance has a dilemma. It's an industry which sells products which nobody wants to buy. Well, imagine you buy an Apple, iPad, and you don't want to open it. Right? Why? Because it's very dangerous to open. You can buy insurance, but you don't want to use it. Why? Because it's all about bad things happening. Right? You fall sick, you have an accident. So insurance has a tough time selling. Right? So what insurance companies are really trying to do now is instead of telling you about the bad times and how to prevent and provision for them, they're saying, how do I prevent the bad times? So how do I drive safely? So that we've built an application for Allstate where it's on a mobile phone. Essentially they track your driving behavior and give you premium discounts if you drive safely. In addition, they also help driving safely, right? And this whole thing is just right now it's in the driving world. It's going to move towards healthcare because now you have all these bands and the Apple Watch and everything, which is going to track your your lifestyle, what you eat, how much exercise you do, and certainly your health insurance premiums are also going to be linked to that. And by the way, it's not necessarily a bad thing. You'll end up being safer, you'll end up living healthier. And aircraft may not fly in bad weather deliberately just because if the insurance is linked to how they fly. Which was what happened with the AirAsia crash a couple of months back. They shouldn't have been flying in that storm, actually. They should have been taking a longer route, but it costs more. So people cut corners. They will not cut corners if they're being tracked. So insurance is getting into that. Large insurance companies are doing this. Lloyd's, who insure aircraft, companies in the driving, in the auto insurance, life insurance, health insurance. Retail. We all have seen e-commerce. E-commerce is essentially disrupting the traditional retail industry. But at the same time, it's changing the supply chain for the entire industry, because every retailer, the traditional retailer has an online segment. But how do I deal with the online versus the shop? I mean, you may be selling, but the shop may not be selling. Or if the shop is essentially a place where people are browsing, and then buying online, how do you link customers to be loyal to you? So blending the physical and the online through loyalty programs, through contactless connection with the customer, through tracking what the customer is looking at and how they're behaving, all that is happening in the retail world. They're also using technology to figure out out of stocks and out of positions of products in the store, things which are traditionally responsible for huge changes in demand. Just because someone's product was not in stock, you sort of lose. So they're doing a lot of that over here. Blending the online and the physical is one area. Manufacturing is impacted hugely. 3D is essentially all about 3D printing, which is additive manufacturing as opposed to subtractive. It's changing, obviously, the whole design of products. It's also changing the supply chain. When you have a situation where an urgent part could shut down one of your lines in your factory, the option of 3D printing it locally just to make sure you meet your demand is there. So before ordering that part from Germany or China, you could just 3D print those critical parts locally. The same thing for other parts of the industry. Smart manufacturing is about the shop floor automation. How do you make sure that the lines are running smoothly? How do you make sure that maintenance of equipment happens without disrupting production? How do you predict downtime of different parts of equipment? And last but not least, and most important, everything is connected. So automobiles, engines of all kinds, machinery of all kinds is connected and is continuously pumping data back. As I mentioned earlier, it can be used for insurance purposes. It can also be used to figure out how people use a particular machine, how people drive in different parts of the world, and use that for better design of products. It's also used for better provisioning for warranty. It's also used for better predicting, and I'll give you an example later, if there's going to be a recall. Suddenly there's something wrong with a particular model. What's wrong? Why? How to narrow down on that, just because you're getting a lot of sensor data from the whole population. Life sciences, again, genome-driven personalized prescriptions. I think we all heard about that. But also connected care. So in many the Uber model is slowly starting to come into healthcare. Much slower than I would like. But essentially the problem with healthcare is that you really need to go to the doctor. And you need to go to the doctor even if all you need to do is spend 5 minutes with the doctor. And essentially that whole business of seeing you versus having to go wait in line, see the doctor, especially for elderly patients, that is starting to get disrupted by having representatives who are trained can go to the home and give a connect with the doctor, and if required. Otherwise, they just report to the doctor. The doctor will just say, this is the advice. So in some sense, that model is starting to happen. I'm seeing it happening in India very slowly, and other parts of the world. Also monitoring in the home, healthcare in the home as opposed to having to go to the hospital. Prevention, making sure that people are taking their medicines properly and living healthily. And finally, society. All aspects of society, from governance, security, as I think here you're well aware, transport, again the Uber model and other areas, agriculture, and lastly, energy. Energy is becoming very important. I'll give you an example a little later with renewables and variability in supply, as well as sensitivity of demand with smart metering and home automation. To summarize, it's the digitization of industry and society. Can someone tell me when I have about 5 minutes or so, right? Yeah. Okay. So I still have a long way to go, so let's speed up. So again, this was digital, Internet of Things, social, big data analytics, mobility in the cloud. And the point I'd like to convince you is that, essentially, analytics today is all about AI techniques. And I think you all agree that it's all about AI techniques. The challenge is that everybody else seems to agree, and that's a huge burden. This is the latest issue of The Economist. Yeah, artificial intelligence. I mean, I would never imagine this. What it does, The Economist, a staid, very numbers-driven publication, puts AI on the cover. That's a challenge, because the danger is that we're going through the late 70s and the 80s, where there's huge hype, and then we're going to have a deep disenchantment if this promise is not delivered. Having said that, there is some merit in what they're saying, but also a huge hype, and we have to be wary of that. But why does big data analytics mean AI? I mean, let me just give you an example. I'm giving this is an old game. Most of you have not too young to have played it. But some of us who have played this game of Pong long back, where you're trying to make sure that the ball stays in play by sort of patting it back, and the red dots are tracking the eye of the player. And this player, if you can see, is doing this. Just look at the red dots, and now look at this player. Can you see a difference between the dots, both players? Any clue? No. Yeah. So see the guy on the left is just tracking the ball. The guy on the right is trying to figure out where the ball is going. And if any one of you were to play this game, what do you think you would do? Which one? The right. A child would play the right game. But business intelligence is all about the rear view mirror. It's tracking where I was last week, last quarter. It's not predicting the future. So how do you do this? Well, the chapters of my book are these: listen, look, listen, learn, connect, predict, correct. So essentially you have to look at the ball, you have to listen to other signals which are coming, you have to learn what happens when it bounces off, to connect the dots which you're getting from different sources, predict where it's going to go, and then correct your action. And that's exactly what you have to do on all of the kinds of AI techniques. You have to have, look is all about search, summaries, exploration, classifications, clustering, rules, subgroups, connection, about fusion and reasoning, inference, forecasting, decision making. All these are things which you all know about. The point is that if you put all these together, that's an AI loop. But there's the other side of it. So that's one thing, that there are all kinds of AI techniques have to come together to make prediction happen. The second thing is, what about big data? How big is big data? The sales pitch is the following: that look, we've been producing this year as much data than has been produced in the past history of mankind. That's a great sales pitch. However, there's a popular, I don't know how many of you follow Kitty Nuggets. Every year it conducts a poll about what's the largest data set anybody's actually analyzed. Turns out that the past 3 years, the mean has not changed too much. In fact, it's gone down. It's somewhere around 10 to 100 gigabytes, and where you are. If you're an insurance company, you're probably in 10 gigabytes range. If you're a bank, probably 100 gigabytes. If you're a car company looking at sensor data, you're probably in the terabyte range. Very few are sitting in the hundreds of petabytes, and you know who they are, right? And there's nobody in between. Okay, so either you're doing medium data or you're doing really big data, and most people are doing medium data. Okay, so what's big about big data? Well, this is what traditional business intelligence does. Suppose you have a whole bunch of customers and you know a whole bunch of things about them, or you have manufacturing plants and you know things about them, or you have days of operation of a vehicle or an engine, And you look at a slice of the data and you say, is there anything interesting happening? Another slice, another report for your manager, another report. That's business intelligence. For the past 25 years, business intelligence has just been about reports. Unfortunately, there are at least small o d to the m cubed, somewhere between d to the m and d to the 2m. If you just work out, it's a little bit of a complicated equation, how many slices there are. That's too big. So it's just 80 attributes, and each of them taking 10 values. That's too big. So even all the 300,000 people in TCS can't spin out enough reports for this. Right? They're just too many. They're almost infinite. And so the real problem is that you can't sample this distribution manually. So big is all about wide data. It's not about the number of points. It's not about how many entities you're talking about. It's about how much you know about each entity. And that's really the challenge. So to summarize, this is before I get into the details, business intelligence itself has evolved from just tracking what is happening, reporting, drill downs, reports of drill downs, why is things happening, what is happening right now, real-time business intelligence as it was called. Thank you very much. Yeah. And then harnessing knowledge from outside the enterprise, listening to things like Twitter, to market reports, risk, etc., fusing information from other parts of the organization, other parts of the world. But really, we're getting to the stage where you need to do AI for BI. And there are two things that you need to do. You need to have predictive and prescriptive intelligence, and need to deal with high-dimensional data. So now I'll talk about some examples of our research. This was more introduction. Again, predictions are all about dealing with data length and dealing with data width. Machine learning, statistics, data mining, all we know about. But I'm going to try to emphasize to you. You've heard about deep learning. I'll give you one example of our use of it. I'll give you one example of our take on visual analytics, and I'll try to emphasize the importance of simulation. That is, that data is not enough. And I think if there's one message you want to take back, data is not enough. I'll give you an example. And these are the research programs I'm going to talk about. I'll go through them one by one. I won't repeat their names over here. But essentially, they're all about different places on this direction of either how real-time your response is and how strategic your response is. The colors are just not coming. Anyway. Okay. The first example I'll take is offer economics. So, all companies have to give offers to customers, to you and me. The offers could be for new products, could be to retain us, could be to upsell, cross-sell, could be various kinds of offers. Could be offers to even in healthcare to take a vaccination. So the issue is who should an offer be made to? What should be in the offer? It's very important. When should it be made? And which offers should be made out of the ones that you have. So I'll give you an example of the economics of this. So clearly you have to analyze historical customer transactions to find out the propensity for somebody taking a type of offer. And there's one example. There's a very interesting challenge in Kaggle. 300,000 customers, whole bunch of product categories. There's also an interesting IchKai challenge, which is currently running. I don't know how many are participating. We are, which is very similar to this. This kind of data is tough. I mean, it's not easy to get the results over here. So you kind of think stuff you get are AUCs in the 6.5, 6.68, 0.7 range at best. And you get this kind of data. So you don't have very good precision and recall. You have lots of false positives, depending on how much you want to tolerate and how much recall you want. The challenge here is then that if this is the best you can do with your data, for a desired cost-benefit ratio, that means the trouble with the offers is, they cost money. So if you're going to give an offer to somebody, it costs you money, whether you're a bank or whether you're a retail company. So you need to have a trade-off. So it's not just getting the best AUC; it's using that AUC to have the best trade-off from the cost perspective. So you have to have a strategy. And finally, what happens in practice? You give an offer, does it work? Well, you could keep giving offers and spending a lot of money and losing money, but you would like to somehow figure that out without having to try out 1,000 different possibilities. If you're Google and it doesn't cost you anything to switch the place of the various ads, it's the people who are paying you are suffering. You just have to somehow keep trying, and you can keep doing it for different customers continuously and do A/B testing all the time. It's okay, but if you're a retail company or a bank, you can't do that all the time. So you have to do simulation. And I think this is where I want to get involved with the whole business of prescriptive analytics. So simulating external factors, the nature of the offer, etc. So I'll try to put a mathematical framework for this. So I'm going to go a little slowly on this one. This appeared last year in IEEE Information Fusion. Traditional modeling is like about you get data from the field and you build a model, and then you have you try to find the best model given the data, right? And then once you have a model, you need to optimize the model, and you basically say what is the given your strategy, what is the expected outcome, and then you have a cost for that, and you try to get the best strategy for that particular prediction. You predict the Y, and you try to get the best strategy, and that's perfectly fine. But the trouble is that one big thing is that the traditional, this is how you do it. You have people who do prediction, they are the statisticians, and then you have the people who decide the strategy. They say, okay, the statistician tells you what's the most likely value for sales of this particular model, right? And then you use that into your optimization, and you say, this is how I'm going to do my production planning. That's not how you should do it. You need to take the distribution and do a stochastic optimization. Big problem. Mathematically very easy. In a real organization, try to get these two people to talk to each other. Very difficult. So big challenge to get the statisticians and the strategists to talk to each other and say what your output is actually input to your optimization. Don't just use your expected values into your LP. Make a stochastic optimization. Very difficult to get people to think about this. But there's much more. If you make a prescription, you actually need to test it back in the field, because that will change your actual data. If you did something new, data will be different. If you're Google or Amazon, you can do this every minute. If you're a retail company or a bank, you can't. So you're in deep trouble. So what do you do? Instead, or what we're saying is you need to do a simulation. You need to have a simulation model which then does a prediction. And you need to essentially make sure that your predicted model you're basically trying to get the best model both for prediction and for simulation, right? So your model should work on your real data as well as your simulated data. And by the way, your simulation model should somehow match the real data, obviously. So this is what I mean by use of simulations. You need to have machine learning for prediction, you need to have optimization, and you need simulation. What kind of simulation? Well, finally, obviously, you need to pump it back, otherwise you're not making any impact to your business. Those of you who do reinforcement learning would see this as very familiar. An enterprise view of reinforcement learning for people who need to take decisions every quarter rather than every minute, as you do in reinforcement learning. So the simulation is where all the action is. So this is all about complex systems modeling. You're modeling all kinds of systems. I'll give you a couple of examples. Offer design, causal modeling, I'll give you an example. But energy markets, suppose you're trying to figure out what's the best time of use pricing. You need to have an economic physics model of people. Suppose you're trying to figure out your campaign strategy. You need to model people like molecules and have an agent-based human-centric model. You want to model faults. You want to see what would happen if a different type of fault were to take place. You have to have a temporal modeling of faults. Discrete event model. If you want to model a supply chain, if something were to go wrong in your supply chain, you need to model that as a discrete event model. So all kinds of complex systems modeling goes into simulation, and that's all depend on different domains. I'll give you a couple of examples. In the retail domain side, you kind of model products in the traditional marketing way, personas. You have different types of identities and personas, and you try to model a whole bunch of people, and you try to say, okay, what's the likelihood that a particular kind of offer or kind of ad is going to result in benefit. This simulation is all fiction unless you try it, but you can use the simulation to drive your strategy and then essentially tune the simulation based on data. Another example is demand and supply and energy. And you have to try to flatten demand. If you don't flatten demand, then your peaks are going to destroy your cost equation. So the whole business is you're trying to have your price versus time, and you're trying to simulate what would happen if different people would shift their loads or not shift their loads. So you try to arrive at a price versus time strategy, and then you sort of have a control system to change your time of use pricing based on demand. Causal analytics is all about prescriptions. So I'll skip this one since we're out of time. So I'll since we're 5 minutes away, I will now have to start skipping a few things. I will now talk mainly about. Okay. So I'm going to talk about the industrial internet quickly, and then end, right? So, like I said, manufacturing is one big area. So, a whole bunch of things are done in manufacturing. So, the industrial internet is all about these connected machines sending data to everybody. I'll give you one example, two examples. One is early warnings of populations, and the other is machine learning anomalies using deep learning. So, traditional reliability modeling is saying, okay, let's look at the failures which take place, and if they are not what is expected, there's a problem. But that requires something to fail in large numbers before you know that something bad has happened. So, but now there's a whole bunch of data coming from all these vehicles. You can actually look at the reliability model which has been augmented by real-time events, so that you get real advanced information into your model, and then you see whether what you're seeing in the field versus what you would expect using standard reliability is different. And if it's different, then there's a potential problem. In practice, we've been able to show that you can actually make very good predictions about the expected number of failures on real data from large automobile companies. But that's not enough. You also need to know why something is failing. So, for example, you want to know, say this is the prediction from the reliability model on the x-axis and the event augmented or the sensor augmented reliability model. Everywhere below the diagonal is something which is failing too early. So you need to find out why that is happening, and say maybe it's from a particular plant or a particular geography. You can do that visually, but you'd also like to do it automatically. You say, is there some subset for which this is happening? That becomes data mining. Right? Last example is a deep learning example, and essentially it relies on the fact, temporal deep learning, that our brain is just continuously making predictions. And when the predictions don't match reality, that's a surprise. And what you want to do is leverage that surprise. So what we've done is you've used LSTMs, which are long short-term memory networks, which are kind of old, and they weren't really used a lot for many years, but now they're coming in very useful. But we've stacked them, so made them deep. And using that, we're able to show that if there's power consumption, you can easily detect when there's an abnormal week. There's a engine. You can easily detect when a normal machine won't have too many failures, but an abnormal machine will have lots of situations where it's very sort of abnormal behavior. And the key here, the key insight here is to look at two things, not just the variable itself, but the control input. And you look at the errors between what you're predicting and what you're actually the errors that you observe in reality. And if those two errors are different, I mean the errors are high, then clearly there's abnormal. But error could be high just because the guy is driving differently. So therefore you need to have the control variables. So if you're driving differently, the errors would be high normally. So then that sort of compensates. So this joint distribution sort of lets you figure out when you're actually doing an abnormal, detect abnormality. This is appearing in the ESANN symposium later this year. So I'll skip some of this and really get on to. I think this is the last thing I'm going to talk about. Yeah. So the very interesting project that we're working on right now is, as a knowledge worker, I want to know. I want to mention this because Bracha has worked in this area. I want to know exactly the information I need at any given point of time. Whether it's from news, whether it's from social media, whether it's from internal systems. So I need to use my social profile, my professional profile, and my enterprise profile to get this information and get insights. We model this mathematically as a recommendation problem. So you need to have probability a particular piece of information is to be retrieved based on models of my context, models of the content, and models of the need. So you put this together in a probabilistic model and have all kinds of information coming into it. And as a result, this is just a quick example. So for example, you're just typing something in email and different recommendations are sort of coming up. We're there, and that's what we're doing. So I'm going to skip some of this. Unfortunately, I had to skip that. And I'll just, oops, last message. Key messages for BI people. You need advanced analytical techniques. Data fusion I was not able to cover. Data mining should be the focus and not reporting. But the one message I want for researchers is that statistics is not enough. Without simulation models, you're not going to be able to do good predictions, because predictions will depend on the data that you've seen. And with simulations, you can go beyond the data that you've seen because you have theory to deal with, and that's science. So you have to put these two worlds together. The science people don't like data. The data people don't like models, but they have to come together. That's one message. The last thing, culturally, people need to share data. People need to realize that clean data is not necessary all the time. You need good enough data is good enough. You need to have business experiments. You don't spend money to test things in the field, never works. So a lot of people say, give me the prediction, it has to be perfect. It will never happen. You have to spend money, deal with false positives, and understand the value of the data, right? Okay. And there's one book, which is out there, one course on Coursera. A lot of stuff is in there. Thank you.
Okay, we have time for a couple of questions. If you can turn the lights on a little bit, so any questions? I guess if no one in the audience has a question, so now it's my duty as the session chair. And as you know, I also had some experience with Internet of Things and data coming from the sensors, particularly vehicle sensors. And it was quite frustrating obtaining those values of the area under curve, which are usually between 0.6 and 0.7. And I always wondered if actually these models can be useful in the field, if this is the best you can get. What do you think?
It's a good point. In the particular case of early warnings, we are able to detect early warnings, because early warnings are really a population level anomaly. When it comes to a machine failure, you're right. Machine failures have a lot of false positives. And so it's very unlikely that you're going to give a very confident prediction of a failure actually going to happen in particular, especially an early failure. That's very difficult. What you can do is just warn people, and then the decision to take whether or not to take a call is up to the person. So, but you have to give them with a confidence, and that's where some of the new work in modeling, which we're just starting to use in non-parametric methods, where you actually give bounds on the nature of the prediction using Gaussian processes. That's where it's becoming interesting. But you're right. I mean, early warnings works fine. Specific machine predictions, more difficult.
It's still hard.
I'd like to hear your opinion about, the recent talking about automatic feature engineering. Do you think it's feasible? Is it going to happen?
Deep learning, right? My experience is that features is, choosing features is everything. Yeah, and if you, I've seen every tool that I've seen. If you throw it junk features along with a few good ones, it'll break. I have not seen a single tool or single technique which is going to not, SVMs are great, but if you throw it a lot of junk features, it'll firstly take a whole bunch of time, and in the end, it all depends on your kernel, and it's never going to get you, you have to do feature engineering. The second thing is when you look at temporal features. If you're looking at time series, if you don't do feature engineering, you're dead. Because you have to look at time scales, some LSTMs, some aggregation, and then push that up with other features. You have to look at some collaborative filtering features. So I don't see any technique which is going to do the collaborative filtering, the temporal engineering, and you just can do the kernel, but you can't do all that together. Maybe it'll come, but it's not there yet. Yeah.
Thank you very much. Hello? Yeah. For mechanical questions, I understand simulating, you spoke a lot about simulating mechanical properties of such at the end. I'm wondering, to go back to what you started out speaking about, retail predictions and offers to send, how that helps when the simulation is just as hard as the prediction, yeah, and equally intractable.
Yeah. So two examples. One in the energy simulation is really simulating the behavior of potential autonomous home control agents in a population where they are essentially mechanical. They're not people. Right? So then you're okay. When you talk about people, what I missed out was the causal analytics or the causal offer design, where you look at not just the who a particular offer was given to and look at the data, but look at the nature of the offer. So the offer could be for different types of discounts and different types of things in conjunction with other types of products. And there are also connections between products. There are relationships between products. Products are bought together. Some are replacements of each other. Some are bought by different types of people. You look at that entire causal network, and then you make some assumptions. Say, if I were to now design an offer which had different 3 or 4 different elements, and then you take out, in the traditional sort of like Pearl's causal counterfactual analysis, you say, okay, take away the incoming links where you make an assumption of what are invariant, and then you can do an offer design based on your data. That's the kind of simulation I would do for offer design, right? So I think you're right. Simulating campaign strategy using an agent-based simulation is still a black art. I would still prefer to do a more Bayesian causal analysis using a counterfactual argument, which still is a simulation because you're bringing your theory in. Right?
Okay, let's thank the speaker.
Thank you.
Again.
Thank you.